Hi guys, good morning. Thank you for joining us for our next presentation. Before we get started, I just have a few quick announcements. One of them is we handed out session surveys on the way in. We really appreciate your feedback, and we'd like to hear from you in order to improve our content and our presentations for next year. We've also got these NVIDIA, we actually call them badge inserts because they fit right in your badge holder. But it's got a copy of everything that's happening in our booth and also other presentations that we're participating in. So please feel free to pick that up. We have presentations happening all the rest of the week in our booth and as well later on today in this room. The last thing I'll say is we're actually live streaming this talk to Facebook. So just keep that in mind if you're asking a question. It'll be on Facebook, and you should check it out when you guys get a chance later on in the show, because all the talks we're doing will be live streamed. Or if your colleagues are back at the office and couldn't make it to Vancouver, you should let them know about it. I think that's it as far as announcements from me. So I'd like to introduce our next speaker, my colleague Jeff Keel. He's manager of graphics tools at NVIDIA, and he's here to talk to you guys about Parallel Nsight. Thank you.
Thank you, Victoria. You know, I guess asking a question at SIGGRAPH is probably one of the least worrisome things you can have on Facebook, right, given all the crazy stuff that people put up there. Again, I want to thank everybody for coming. I'm going to give you an overview of Parallel Nsight. Can I get a quick show of hands of folks that have heard of Parallel Nsight? Wow, most of us. Okay, excellent. For those of you who haven't, Parallel Nsight is really a tool for GPU development. It helps with both the graphics side of the house as well as the compute side of the house, or the CUDA side of the house. And what I'm going to do is I'm going to give you an overview of CUDA itself, of kind of what's going on with CUDA lately, with our latest 4.0 version. And then I'm going to go through a massively long demo of how you use Parallel Nsight to solve problems and fix bugs in both CUDA as well as in your graphics applications. As far as CUDA 4.0 is concerned, a lot of great features went into CUDA 4.0. And I kind of categorize them by three main categories. The first one is we really tried to make things a lot easier from the programmer's perspective. We had issues with past versions with things like you can only use certain GPUs on certain threads, and the context migration, thread migration was difficult. So we tried to really clean that up to make it just a lot easier. You no longer have to worry about which context you're going to use on which thread. We want to add full support for C++, so now you can do new and delete on device. You can do virtual functions on device. So a lot of the same types of capabilities for polymorphism and all that you have on your CPU, now you can do on your GPU code. Also, we support inline PTX assembly. PTX is basically our agnostic, our GPU agnostic assembly level. And so if you really want to write things to as close as possible to the metal, you can write that in PTX assembly. And the great thing is it doesn't matter if you're on a Tesla GPU, a Fermi GPU, or one of our next generation GPUs, one of our Kepler GPUs, all that will just work just fine. So it's kind of that happy medium between writing C code and then writing, directly to the metal. Couple of libraries that we put out there. The C++ template performance primitives libraries has lots of great functions in there to do sorts and reduces and things like that, as well as the NVIDIA performance primitives libraries. It's a lot of image processing and video processing. So on the second item is really just trying to make the multi-GPU programming faster. Obviously, when you're on a single GPU, you're as fast as possible. Just load everything into GPU memory and bang, 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 you're going. One of the things that we did was we introduced a unified virtual addressing scheme. So now you can have one virtual address space across all of your devices, and the runtime takes care of any type of syncing you need to do between them. Another thing we did was we now have GPU Direct 2.0, and what that does is rather than have to have a buffer start on one GPU, come down to the CPU, and then go on to your second GPU, it actually just communicates directly from one GPU to another. And so it still goes over the PCI Express bus, but it's a lot faster. It doesn't have to do that round trip through the CPU. So if you do happen to do some shuffling of some buffers, it's going to behave a lot better. And again, with the unified virtual addressing, you don't even have to worry about it. If you access that buffer on the secondary GPU, the runtime takes care of making sure those are synced properly. And then we've got some other developer tools for those folks out there that are working on Linux and Mac OS. Of course, we've got the CUDA GDB debugger. It's a GDB-based debugger that allows you to do debugging of your applications that are running on the GPU, as well as our visual profiler. And we had introduced some new capabilities, our automated performance analysis tools. And so it does some automation of analyzing the data to give you feedback on some things that you can do in order to make sure your GPU code is running as fast as possible. So Parallel Nsight is basically a tool that runs on Visual Studio, and it's a plugin into both Visual Studio 2008 and 2010, and it allows you from the same development environment that you're used to build, to debug, and to profile all of your GPU code, whether it be CUDA code or graphics code, DirectX 10, DirectX 11, and even some features in OpenGL, which we'll talk about in just a little bit. And the great thing is it's all just completely in Visual Studio. So you don't have to sit here and shell out to a different program or start a different program or anything like that. It's in that same development environment that you're used to. And especially when it comes to the debugger side, all of the capabilities in the debugger use all the native Visual Studio tools. So the memory windows, the watches, all that kind of stuff, they work just the same as they would when you're debugging on CPU code. So our three main feature sets that we have. First, we've got the system analysis, and these features work on both CUDA and graphics. It allows you to view the CPU and the GPU events along a single timeline. So you can see things, work that is being launched on the CPU and how that's going to launch work on your GPU. And I'm going to give you a great overview of it in just a minute, but this is just a quick little synopsis. Also allows you to, again, see those workload dependencies. You can see the function calls on your CPU that are going to launch kernels or maybe launch draw calls in DirectX or even OpenGL on your GPU as well. Again, these support CUDA, Direct3D, and OpenGL. And also in the system analysis, you can do profiling of your CUDA kernels using some of our performance counters that are available in our hardware. And so you can get things like how busy the GPU was, different statistics on how many instructions were used, how your branching was doing, if it was divergent or not divergent, and things like that. So it just really enables you to get those vital statistics to fine-tune your kernels. On the debugger side, as I touched a minute ago, again, it's completely integrated into Visual Studio, so it works exactly as it works on your CPU debugging. We support GPU-accelerated CUDA and HLSL debugging, so all the code that you're running is running on the hardware. It's not running in emulation or anything like that. It's all running on the hardware, so when you hit a breakpoint, the breakpoint is being hit right inside the GPU. And also, you get to look at all of your threads as they're executing in parallel. So you don't have to worry about any issues of synchronization or anything like that. Or you don't have to worry about removing issues, I should say, of synchronization. So you can truly debug problems as they're coming up, running live with your thousands upon thousands of threads that are running. Again, all the conditional breakpoint capabilities, memory viewers, all that. On the graphics side, we've got our real-time inspection of the D3D API calls. This allows you to do the scrubbing through your scene to kind of watch your scene being composited, as well as looking at all of the D3D API, checking every single API call, making sure the settings are set the way that you expected them to be. Also, you can again, you can do the GPU pipeline state. Also, you can do the pixel history capability. This is really great because it helps you to understand what are the contributing fragments to a given pixel on the screen. Because you never know. It could be something that a fragment was improperly calculated. It could be something in your blending that's not set up properly, so that when it blended it didn't get computed properly. So you can just really see every single fragment as it's generated, and then you can actually debug that individual fragment. And again, I'll show you a demo of that in just a bit. And then finally, in the same way that you can do the profile of the CUDA kernels in the system analysis capability, we allow you to do the profiling of your frames inside the graphics inspector. And so you can look at every single draw call in your entire frame, get an idea of what the bottlenecks are, how it utilizes the GPU, how it contributes to the scene, and you can really pinpoint exactly what a bottleneck is, whether it's ALU bound, or if it's texture bound, or if it's blending bound, or if it's frame buffer bound. Rather than running a bunch of different experiments, you can just simply run this profiler and it'll tell you for every single draw call what's your bottleneck. And I do want to emphasize, this is all free. We did have a licensing scheme in the past. We decided to just get rid of that. We really wanted to make sure we got the tools in your hands. And so all these licenses are completely free. All we ask is for an email address. And actually, I think you can even skip that if I recall correctly. Everybody's happy about that. Good. Glad to hear that. We're happy about it too. So I did want to give you a quick overview on how to get things set up. And this is important, and I want to get some feedback when I get done. So one of the ways that you can use Parallel Nsight is if you have one computer and a single NVIDIA GPU, that enables you to do the system analysis capabilities that I talked about, as well as the graphics inspector. So being able to look through all of the draw calls and look at all the D3D API state. It's just real simple. You just install the appropriate NVIDIA driver. It's just one of the web drivers. It's not a special instrumented driver or anything. And then you install the parallel Nsight hosted monitor on that machine, and you're off to the races. Now, another setup you can do for you CUDA developers is if you have two NVIDIA GPUs in the same machine, that enables you to do CUDA debugging on a local system. And so what will happen is all of your Visual Studio and your desktop and everything will be running on one GPU, and on the other GPU, your CUDA kernels will run. And so we can stop that secondary GPU, and you can inspect state and memory view and all that kind of great debugger stuff while you're still updating that other GPU. Because the whole idea is once we stop the GPU, it's stopped. So you can't do refreshing of the desktop or anything like that. So we got to have multiple display capabilities in some way, shape, or form. So again, when you have two GPUs in a single machine, that's going to enable that CUDA debugging. The next one is if you have multiple machines, and that's actually the system that I have set up here. You can have a host be any type of machine you want, connected via network to a target with a single NVIDIA GPU. Once you have that installed, that's now going to enable the graphics debugger. So that same CUDA stepping of CUDA code, now you're going to be able to step through and inspect your HLSL code. And also the pixel history capability is enabled once you have this multi-system setup. And then finally, we've worked with HP and Parallels, and there's a capability of taking a single system, putting multiple GPUs in there, but you assign a guest OS to that second GPU. And so we've got our primary GPU running the host OS, then I have a fully hardware accelerated guest OS on that second GPU. And so that one obviously is able to stop at a breakpoint and you can inspect it from the host OS. And so that's another capability that we have. So a quick show of hands though, for the capability of being able to do the debugger, is it difficult to have multiple GPUs? Who here has a problem having multiple GPUs or multiple systems? Just one or two? Okay. Three. Because there are some other things that we're looking at in terms of wanting to improve that. You probably have heard of our latest technology, well, latest, it's been up for a while, Optimus, which allows you to have some sort of motherboard GPU, be it Intel or whoever, and then you can have a discrete GPU as well. And what we do is we actually share the desktop between the two GPUs. And so we've already done some preliminary testing on CUDA, and that works actually just fine. So you can actually have your Visual Studio running on that integrated GPU, and then the discrete GPU can be running your CUDA kernels. We haven't done much testing on that with graphics yet, and it's something that we're pursuing, but that's another possibility if that multiple GPU or that multiple system setup is a problem. The way we look at it also is it's kind of similar to doing console development. If you have console development, you've got your host CPU, and then you've got your device, either your PS3 or Xbox 360 or whatever. So that's kind of similar to the setup you've got there. All right, well, let me go ahead and run over to the demo. If we can bring up the host, please. All right. So this is Visual Studio, and obviously, and what I'm going to do is I'm going to show you real briefly how to set up Parallel Nsight. So I'm going to be doing a. Actually, you know what? I'm sorry. Go back to the. I forgot a slide. Go back to the slides, please. Jeff, slides, please. Thanks. I got thrown off by the big picture. Apologize about that. So this is a demo called FFT Ocean. It's from Calvin Lin from NVIDIA and John Jansen. And what it is it's a simulation of a wave in the ocean, and it uses CUDA to do the computation, and it uses DirectX to actually do the display. And so to give you a quick overview of what that's about, it uses the algorithms that were developed by Jerry Tessendorf from his paper Simulating Ocean Water. It is a statistical-based model. It's not physics-based. And the idea is it basically generates a bunch of sine waves and makes that into a displacement map. And then we use FFTs and bring that over into DirectX to actually polygonate, make polygons out of it and then display the ocean. This is a technique that's been used in the past. Movies use it a lot. They use fairly large maps, 2K by 2K, probably 4K by 4K. In games, they've used it in the past, mainly doing it with a CPU side simulation, so the maps are very small. So obviously you'll get a lot of tiling, like a 64 by 64K. The version that we've got here runs about 512, so it's about medium-sized maps, so you get a really, really nice look. You don't get a lot of the issues with the tiling. And again, it's just basically hybrid sine waves, Gershner waves kind of thing. So. And to give you an idea of how it works, let me see if I got my pointer. Excellent. How it works, I did a quick snapshot from our analysis tools. I'm going to explain all this in detail in a little bit, but I just want to give you an overview of how the demo works. So right here we've got what are called D3D perf markers for you guys who are DirectX fans. And what I did was I instrumented my scene and showed the different areas that are being rendered. So you can see I've got the simulate the water, the rendering of the terrain, and then that includes both some mountains that you saw right there. And so those are the different components of my scene, including the rendering of the HUD and everything. Now what happens is we go ahead and do the wave simulation on CUDA, and so these lines are showing all my CUDA kernels that are being displayed, CUDA kernels that are being run. And then I've got my DirectX 11 kernels, DirectX 11 draw calls that are being run. And so it kind of does a nice pass-off of the buffers. Now, the great thing here is that there is no mem copying going on here. The buffer basically gets computed by CUDA, stays on the GPU, and then DirectX just takes that exact same buffer and uses it as input for its draw call, for its geometry. Okay, now we go over to the host, please, Jeff. So in order to set up Parallel Nsight, the first thing you want to do is come into our settings page. And this is actually all automatically populated based on what's in your project settings. You can also override that if you want to launch a separate external program. I'm actually going to start here on this second page. What the second page allows you to do is allows you to synchronize your data, be it your executables or any assets that happen to be part of your program, from the host to the target. And so that can be really useful, especially if you have smaller like demos and things like that. You don't have to worry about duplicating those or maybe using a shared drive or something like that. We can actually take care of sharing those between those two. And it's a smart copy, so if the data is already there, it won't bother copying it over again. And it's really useful if you're doing kind of iterating on things. You're changing some code, changing some CUDA code, whatever, and it can just push things over really quickly. So it's really nice to be able to use that. And obviously we support whatever directories you want to synchronize, and then we can exclude extensions, things like precompiled headers and stuff like that. You don't want to be synchronizing those over. So once you set up your synchronization, and by the way, if you choose to unselect that, then all of the directories that we set up here are going to be local to that remote system. So it's going to be from the remote system's perspective. So again, if you have already got a shared drive or you've already got things installed the way you want it, all you have to do is just disable synchronization on this page and then just say, C:/blah, wherever your things happen to be. Then you just simply specify your connection name, any command line arguments you might happen to have, and then a working directory. So it's real straightforward to be able to run that. Now I'm going to warn you ahead of time, we've had a couple of networking issues here. And it looks like, of course, it's going to bite me. Unfortunately, we're having an issue with the handshake sometimes when we first start the debugger. And so the first time, sometimes it decides it's just going to time out and not let me go. And I will just rerun it in a second. If it will eventually time out, there we go. All right, great. And if you would bring up the target, please. So I just went ahead and launched. Now I'm showing. There we go. I'm showing the application running on the target system, and you can see that I've got a problem here, don't I? The waves aren't looking too good there. Well, that's what we have Parallel Nsight for. Yes, I admit it's a little bit contrived, but nonetheless. So the idea here, though, is that your application's running here on the other system, and now I can go over to the host, please, and try and figure out why do my waves not look right. So let's go look at my kernel that I've got running. So here's my kernel that I go ahead and do the update of the height field. And I'm going to look through here. Well, let's just go ahead and put a breakpoint in here. I'm going to hit F9, standard breakpoint stuff. And I've gone ahead and stopped at my breakpoint. I can lift up this guy a little bit. And you can see that I have my autos and everything. So all my auto windows are populating. You can come into a watch expression. You can say, I don't know, oops. I'm not a good typist. Oh, you know why? I'm a really bad typist. There we go. So you can even do, basic mathematical expressions and stuff like that. So it's exact same stuff that you would expect in Visual Studio when you're running on CPU code. You can do right here on the GPU. And so I can step in, step over. I can come down here and I can say, run the cursor, or hit F7, all that kind of same stuff. So, and all this is running on the GPU. And I can show you one of the great things you can do is you could look at the device summary. And what this gives you, let me move this down just a little bit. What this gives you is all of the blocks and warps that are running on the GPU, and so you can even change which warp you're focused on just simply by double clicking there. So it's really great to be able to kind of get an overview of all the threads that are basically running on the GPU and inspect the different variables. And you can see right here my watch window went ahead and updated because I changed which thread I was looking at. So it all kind of works naturally as you would expect it to with things that are running over there on the GPU. Well, let's look a little bit closer here. I'm kind of wondering now if I might have an issue with some normalization. Yes, you probably figured I know what the problem is. So what I want to do is I'm going to put a breakpoint here, and I'm going to set a condition on that breakpoint. Actually, let's remove my first breakpoint. And I'm going to set a condition on there. And I'm going to say, I'm going to try to check out if my kx and ky variables are out of range. So I'm going to say kx less than or equal to negative 1.0 or kx greater than equal to 1.0. And hit F5. And you can see, yep, indeed, that's the problem. So what's happened here is that I'm computing my offset, computing my normalized coordinate, but I forgot to normalize it. Pretty straightforward, something we probably all have done. That and the infamous cut and paste bugs are probably the most famous ones. So I'm going to I'm going to exit the application on the target. I'm going to come in here and on the fly see if I can fix this bug. And it looks like I already computed my reciprocal square root. I just was silly and didn't use it. Oops. And then edit it for ky. All right, now I'm just going to compile. So I just went ahead and updated that to now go ahead and normalize my kx and my ky. It's updated. And I'm going to start my CUDA debugging. And, of course, it's going to time out for me this time. I wish I had a good song and dance for when this happens, but I'll take a drink of water. How about that? There we go. All right, now if you'll show the target again, please. And it's going to come up, and there we go. Our waves look happy again. All right, let's come back to the host. I want to show you a couple of other really cool features that we've got here. So what I want to do is I'm going to come down here. This is where we actually update the displacement map, and we input some different features like a choppiness scale and some other capabilities there. And I want to show you some other the ways that we've got things integrated well with Visual Studio. So one of the things we will allow you to do is come here and grab the memory window. So I can just grab this displacement variable. And right there, boom, it's now displaying that buffer that is actually on the GPU. It's displaying that memory buffer here. And now the cool thing is all the same capabilities that you've got in Visual Studio just work. So I can now cast it to a float, and now I can see all these float variables that are in my displacement map. So everything is completely integrated into Visual Studio. Another really cool feature that we have is the ability to show you the disassembly. So I can come down here and show you the disassembly window. And what we show you here is this is actually, remember earlier I was talking about that PTX code? And so this is the same exact disassembly like you'd have in x86. Well, this is now your PTX code that's running inside of Visual Studio, and you can step through that PTX code and everything. So if you want to be, again, doing that inline assembly with PTX and debugging it with Visual Studio, you can do it just like you did on the CPU. So it all just works great like that. I also showed you the device summary. One of the other things you can imagine you want to be able to do is when you've got all these threads running, you want to be able to change the focus. You want to be able to change which thread you're looking at. And so what we do is we developed this debug focus window, and it basically shows you the dimensions of your blocks, how many blocks you launched, and also how many threads are in each block. And you can come in here and you can just simply change, and it tells you what your valid indices are for each one. And this is another way that you can use it to simply change change what thread you're in. And you can see down here, our locals window now is changed to update to that thread. So if if maybe you're doing some screen space stuff, or you know exactly which thread you want to be looking at, you can just quickly change to that thread and know exactly and know that you're looking at exactly the thread you're interested in. All right, I'm going to go ahead and close this out. The next thing I want to do is I want to show you an analysis run of this application. Now, in order to save time, I went ahead and pre-did this, but I'm going to show you how I did it, how I got it set up and everything. So all you do is come here to the Nsight menu and just say New Analysis Activity. I'm going to show you all the capabilities that we've got here. So similar to our other Nsight setup, you can set up your analysis capability here. The reason why you might want to do this is you might want to run a release version instead of a debug version or whatever, so you can set up all your parameters there. You can specify whether you want an application trace, a system trace, or a profile run. Now, an application trace will focus just on your application, whereas a system trace will actually trace all of the applications that are running on your system. So you can maybe find out if that hit you're seeing or that performance problem that you're having is maybe not even caused by your code, it's caused by some other application that's running. Then once you get your trace set up, you can figure out what things you're interested in tracing. So at the system level, you can do all of your system CPU traces. We have a tools extension which allows you to decorate your code with both ranges and individual markers. And so you can annotate what's happening in the analysis section so you can get a feel for, okay, well, but what does this mean relative to what's happening in my code? And you'll see why that's important when I show you this with the example that I have here. Then in CUDA, you can do API tracing as well as workload tracing, so you can specify which API calls that you're interested in. Then we have the same capability for OpenCL, all the API calls and what have you. Then in DirectX, same thing. You've got API capabilities as well as what workload tracing you want to do. Also, for all you OpenGL programmers out there, those same exact capabilities are available in OpenGL. So if you maybe are doing OpenGL and OpenCL or OpenGL and CUDA interop, you can do that same tracing right here. You can get some really great performance information about what's happening on your GL program. And also we do the same thing with the CG API, if you happen to be using CG. So once you do that, you're going to come up with one of these NV reports. And when we first start out, what we do is this is basically just kind of an overview of what happened with your application. And so this is the application that I actually ran, where it was running from, what machine it was running on, how long the capture took, as well as the different files that were generated. Then for all the CUDA devices, it gives you information about the hardware that was installed on that machine. So again, you can figure out, oh, this was a lower-end GPU or this was a really high-end GPU, so you can kind of get an idea of what to expect as far as what the performance information should be. Next, we show you all the CUDA kernels that happen to launch for that one. And then we've got information about your DirectX performance markers and some more system information. I want to show you just a few pages from this one. I'm going to start out by showing you the CUDA launch summary, the CUDA launches. This is a really great page because what it does is it gives you every single CUDA kernel that was launched in a big list, and it gives you all kinds of great statistics, the start time, the duration, the occupancy. Now this occupancy calculation is basically an idea of how full was the GPU. And there's a lot of different things that can impact how many threads that can run on the GPU, including things like how much local memory do you use, how many registers are you using, just different types of characteristics of your kernel, and also obviously how many threads you happen to launch. So you may not be launching enough threads to even fully occupy the GPU. And so what you can do is you can click on any given launch, and you can come over here and see that if I vary my block size, if I vary the number of threads that I'm launching, how close can I get to the total occupancy of the given GPU, if I vary my register count, if I vary the amount of shared memory I use. And so this is great to be able to kind of fine-tune your kernel and or your launching to make sure that you're really filling the GPU with all the data that you want to fill it so you can get things computed as fast as possible. Another thing I want to show you was the memory copies. And so this obviously can be a significant source of performance hit, especially when you're doing lots of copying of your buffers back and forth from the host. And so you can see here at the very beginning, and this is from this application I was running earlier in case I didn't mention that. So you see at the very beginning, I went ahead and copied a couple of buffers from the host to the device, and then everything else stayed on the device. And so all my memory copies are on device, anything that I happen to be copying from one buffer to another. So that means I'm really able to use the GPU as fast as possible. I'm not getting hurt by that PCIe traffic and things like that. The last one I want to show you is over here on the timeline. And this is what I showed you earlier when I kind of gave you a quick overview of what's happening in the application. And this is really great because this gives you an overview of both the system level as well as your application level. I'm going to start at the system level. You can see down here I'm on a 4-core system, and I'm going to zoom in real quick. And I can see at a glance how occupied every single core was. Now, if the little bar there is showing green, that means it was running your application. And obviously, these gray bars are going to be running some other process. And then once I actually go down into the cores, I can actually see what they were actually running. So I can see here, obviously, this is my application that was running, but over here, you know, I've got SVC host. We've all seen that far too many times, I'm sure. And then tooltip over this guy, maybe this guy. Zoom in a little bit more. There we go. And this is SVC host again. Okay, so that's some other command. So you can see all the different applications that happen to be running on your system at any given moment. And so you can see, obviously at a glance, you can see, am I CPU bound? Am I tending to, are all these guys maxed out and therefore, you know, I'm completely CPU bound, or am I more GPU bound? And obviously you can see here as well that, you know, once the application starts, this is probably the loading time right here. Once the application starts, these other 4 cores are really not doing a whole lot. I'm fairly well GPU bound on this one. So I'm going to go ahead and close that. Open up this, and then what this is going to show me is every single thread that was running in my application. And you can imagine that a lot of these are probably things that are not doing a whole lot of useful work at that moment. So we can filter these and basically just say, okay, give me only the ones whose, you know, core percentage is like 0.2. And that's really going to allow me to kind of drill in on the thread that's doing the significant amount of work for my application. And you can do that based on a whole bunch of different capabilities there. So I'm going to start by showing you again these perf markers and tools extensions. So you can see I've got a whole bunch of frames going here. I'm going to zoom in on just a few frames. I'm going to grab 3 frames right here, okay? So these are my Do3D perf markers. Again, this API has been around for a long time. It allows you to instrument ranges and different events that are happening in your DX code. And you don't even have to be using DX to use it, to be honest. And so what I did was I instrumented it to show this is when I'm rendering my scene. And again, this is when I'm simulating the water, rendering the terrain, rendering the water, rendering all the HUD and everything. And then what we also did was we instrumented just the CUDA part using our MB Tools extension. And so we can see here, let me go ahead and zoom in a little bit closer here. You can see here I've got, you know, this is the entire range when I'm doing compute. I'm updating the height field. First I do the updating of the HT, and then I do the inverse FFT, and then I go ahead and update that displacement texture. That was that last kernel that I was showing you. And so you can see here at a glance kind of what was happening, and it gives you that context of what was happening inside of your application. Now, if I open up these 2 panes, I can actually get an idea of what's happening on the GPU as well. Well, CPU and GPU, because we're showing both the API calls as well as the GPU calls. And so you can see here that when I was updating my height field and doing my FFT and updating the displacement map, that's going to launch all of these different kernels on the GPU. So this is actually different workloads that were happening on the GPU. You can get an idea of when it stopped and when it started, how long it took, all the different information about it. And the cool thing as well is that you can do the same thing with DX. Now, the thing that you can see here is that, you know, right now I've got some concurrent kernels going, so I've got, I guess, you know, 3 or 4 different kernels going. But actually, when I'm running in DX, I can get an insane number of draw calls happening at the same time. So I'm just going to grab just this last portion. Probably just zoom in here because this is where it shows it the best. And let me extend this height just a little bit. So these are all draw calls that are happening concurrently on the GPU. And I don't even know how many, 15, I guess. You know, at one point we have 15, maybe even upwards of 20 draw calls. And they're all happening concurrently on the GPU. This is really important to remember, and I'm going to come back to this when we come to the frame profiler. Because what's happening is that you can see here, this top draw call is going to take, you know, some amount of milliseconds. How many is it taking right there? You know, 370 microseconds, okay? Now this draw call that's right below it, it really only adds, you know, what, 2 or 3 microseconds to the overall frame time because it's going to run concurrently with this first draw call. So when you're looking at the frame profiler for graphics, a lot of people will get confused because they will try and add those numbers up and say, hey, wait a minute, it doesn't add up to my total frame time. Well, the reason why is that we're giving you this amount of time. We're giving you the amount of time each draw call is taking, but since they're running in parallel, the overall frame time is not going to be the addition of all those. Now we've got some capabilities in our next version that'll help that to understand that a little bit better. We're going to show you both the overall time, just like we show you now, but we're also going to show you the incremental time. So as you add new draw calls to your scene, you can determine how much does it actually impact my overall frame time. And it could be that some of them effectively go for free, because you're bound effectively by one large draw call, and you can add 3 or 4 different draw calls, and it doesn't really change your frame time much at all. But this is really good to be able to show that capability. And then finally, there we go. And then finally, I just wanted to show you a little bit more of the API level trace. And so you can see here's the API calls that I'm making for CUDA. And this is a CUDA launch, and you can see right there, it goes ahead and launches that kernel. And again, you can watch those kernels happening. So you can see that connection from things that are happening on the GPU to things that are happening on the CPU. And then, yeah, you have the exact same thing here in DirectX. So I can see all of my, let me zoom in even further. I can see all of my different draw calls and clear calls. There's a draw call right there. Draw index call, draw index call. So you can see that exact same thing. These are all the calls that are happening at the CPU level for DirectX, and that's going to result in all of this work happening at the GPU level in DirectX. Okay, great. Now what I want to do is I'm going to switch over to graphics. And I'm going to bring up a different project. And this is our aliens versus triangles demo. This is one that's been out for a little bit. And of course, it's not going to connect it the first time. Actually, while I'm waiting for this to connect, do I have any questions on the CUDA side of the house? Any questions about what we showed here in the CUDA? So we can utilize this time better? Yeah, in the back, yep. Yep. Okay, so the question was, if I happen to have multiple GPUs set up an SLI, so I've got that SLI bridge going across it, can I use that bridge in order to copy from a buffer from one GPU to another? Unfortunately, no, not at the moment. It is something that we've considered in the past. It's kind of a specialized bridge. It's not a generalized link between the two. We mainly use it just for that scan out for SLI, but it's something that we could potentially look at in the future for sure. Okay? All right, if you would bring up the target, please. So this is the application that I'm running. This came from our demo team at NVIDIA. And what I did actually is I went ahead and did a single frame capture. Now you can do this with the application running, and you can pause it while the application is running and do all the capabilities I'm doing here. I wanted to show something a little bit different here. What I did was I did one of those pause and captures, but I saved that capture off to disk, and now I'm actually loading it up. And this can be really useful if you happen to find like a rendering problem, even if you have a problem with our drivers, or if you want to, maybe a performance problem, I mean, you want to share that with a colleague, you can take one of these captures and either send it to us or send it to your colleague, and they can see the exact problem that you were seeing. So it's really useful to be able to imitate things and make sure that you're giving them the exact setup that you had when you saw that issue. So all the capabilities that we have here on the host, we have these graphs right here. These are real-time graphs that are giving you feedback from the GPU on what's happening. So this top graph, I've got a GPU busy, which you see we're right at about 100%. We've got how busy the geometry unit is, how busy the ROP unit or the blending unit is, and how busy that shader unit is. So it gives you an idea. Our shader unit's probably, about 30% busy. Our blending unit's probably about 20% busy. It looks like we're doing a whole lot of geometry, and that makes sense. I mean, we've got, actually, I can even show you in just a second a wireframe of that. Oh, that's right, we do the, I'll show you that in a minute then. Hello. There. We've got displacement, tessellated terrain going on here, and this guy is tessellating. He's actually done with multiple passes, and so it makes sense. We've got a whole lot of triangles that are being rendered, so it makes sense that our geometry unit is the one that's most taxed there. Down here, I've got a graph there showing a couple of CPU side things, CPU side statistics, including the total time for the frame and, the total time for the driver, as well as the total amount of time the driver spent waiting for something to happen on the GPU, and that's in milliseconds, I believe, no, microseconds. And then down here, I've got, again, my vertex count, the number of vertices. You can see I've got bazillions of them, and then the number of primitives that I've got drawing. And these are completely configurable on the host. You can specify whatever GPU counter or CPU counter you want, and you can, move these around and, change their size and all that kind of stuff. A couple of other things that you can do here on the target is we've got some of those same kind of targeted experiments. You can do a 2x2 texture. and get an idea if you're texture bound, kind of standard stuff. We also do what we call a min geometry. So what this does is this does everything on the CPU side, but then every draw call it submits with only one triangle. And so the idea here is it helps you to see if you're more CPU bound or GPU bound. If your frame time wouldn't change here at all, that means you're probably CPU bound. But you can see our frame time change, so we're definitely GPU bound in this case. So what I can do now is I can just hit the space bar, and now I can go into pause and capture mode. And I'm actually syncing on the host, and I'll demo that for you in a second, but I wanted to show you the capabilities that you've got here on the target. So if you've ever used perf HUD, one of the capabilities that we had there is the ability to kind of scrub through your scene and watch things being composited. And that's the same capability we have here. Now, this is a deferred renderer. So this is our G buffer pass that they're computing all those normals and what have you. And this is a shadow pass that they're going to do. And then they actually do the compositing. And then they're going to do some special effects, some blurs and what have you. And then towards the end is when we actually do all that rendering for the HUD. And so you can kind of just at a glance get an idea of what's happening with your application. This is really useful. We've also had a lot of feedback from developers where they said that this was helpful for especially showing artists how the engine works, because they're thinking in terms of visual. That's where their mind is always focused. And so this really helps them to see, when you have this piece here and this piece here, this is how the scene composites, and really helps them to get an idea, and it allows them to free up their creativity once they see how your engine works and how your application actually works. Now up here we've got all of our perf markers that we had. So we've got, again, we're showing that writing the G buffer pass and doing the orthographic projection, and then you've got some subs here as well. And then you can see here at each individual draw call, we can show you all the parameters for that draw call. Now, one of the problems you can have is I've got probably a 1200 wide screen here, and I've got more than 1200 events. So if I hit the space bar, now that's got me where I've got the shift key, that's got me where I've got one pixel equals one event. An event is basically an API call. And what we do is we highlight in blue the API calls of interest, things like clears, draw calls, things that are actually going to make a difference to the scene. We go ahead and highlight those in blue so you can see exactly what those are. Some other capabilities that we have is right now you can just grab this render target and start zooming in. So you can inspect what's happening in the render target. You can hit the control key, and we've got a little magnifier, so you can inspect different values that are in that render target. I'm actually going to move back a little bit further to where I have a couple of different render targets. And you can grab whatever render target you want. This is that normal map, and I can grab a different render target. This is my diffuse map, and again, just zoom in on it with the mouse wheel and everything. Now also, one of the things we added in 2.0 is we also give you the textures that are currently bound, again, in order to give you an idea of the context of that draw call. And again, you can just click on them, zoom in, do all you want, just be able to inspect all the state right here on the HUD to give you to give it to you in context in your application while it's running. All right, let's go ahead and switch back to the host, please. So you saw on the bottom there, on the target where I had all my perf markers. Well, now I've got my frames page, and this again shows me all of those perf markers that are in my scene. And so, yeah, that's basically that. Now what we have up here is we've got all of our draw calls and again those events of interest, and I can zoom in here and select an individual event and be able to see what all the information was, and I can actually see synced from the target to the host. This is actually an image of that render target that was computed on the target, and then we synced it over to the host for you. So what I want to do is go ahead and dive in and show you some of the really cool features that we've got in our draw call page. So once I select a draw call, I go ahead and click on the inspector, and now it's syncing all of the textures and the render targets over, again, at that moment in the frame, from the target to the host. And I've even got the geometry. So I can sit here and inspect the geometry, make sure that it looks exactly the way I anticipated. I can select a texture. I see all the MIP levels that are in that texture. I can even select an individual MIP level. If you have a cube map, it shows you all the cube map information, as well as all my render targets. I could do the exact same thing. So it's going to synchronize that render target from the target to the host. And then I can come in here and I can zoom into the render target. Now another capability we have is you see up here this navigation bar. We do support breadcrumbs and cool stuff like that, so you can just hit back whenever you want. You can come in here and you can go to a specific page of information that you want. You can look at any one of your bound textures, any one of your bound render targets. I can come in here and go right to my pixel shader page. And now I can see all the information about my pixel shader. I can actually open up the shader And this is all the source code that was running for that draw call. So you know exactly what pixel shader was running when you were running that draw call, all the different buffers that are bound and what have you. So all the information you could need to be able to inspect your state, make sure that it's set up exactly as you want, make sure you got your constant buffer set exactly as you expected it. It's all just right here at a glance. You can do the same thing with your output merger. You know, check all your render targets, all the render target views that you've got, make sure you've got your depth stencil view set up properly and what have you. So all that capability is just right there. Next thing I want to do is one of the capabilities that one of the problems that you can have when you're doing rendering of graphics is you get that one pixel that just doesn't seem right. And you can imagine that we could come over here and we can go to our shader window and somehow amongst my 125, and this is a tiny app. We've seen applications that have literally 5, 6, 10,000 shaders. Figure out what pixel shader was that actually impacted that pixel, that created that fragment, that changed that pixel. That's kind of useful, but it'd be really tedious after a while. So what we did was we came up with the idea of using a pixel history. So what you do is you click your render target, and then you just say pick pixel. And I'm going to pick a pixel on my render target, and it's gone ahead and run an experiment using our debugger capabilities on the target to figure out all the fragments that actually contributed to that eventual pixel. And so you can see here, here's the draw call that was happening for the terrain, and then here's the draw call that was happening for the character. And so I can say, okay, what was my render target before it started rendering? Then what was the render target for what was the value for this fragment? And then what was the render target after when it blended with that fragment? And that's really cool. So now I can figure out, okay, where would that funky pink color or that really wild black color or wherever, where did it come from? I can see exactly the draw call. And the great thing is I can come in here and I can just click the draw call and I can see exactly what the information was that was bound during that draw call, because maybe it was an issue with the blender or something like that. Now the other thing we can do is maybe you figured out, okay, the D3D setup is okay, but man, there's just got to be something wrong with my fragment shader or my pixel shader. So now I can just say debug pixel. And it's gone ahead and put a really complex, and I'll show it to you right here, a really complex conditional together so that you can figure out exactly that pixel, the exact fragment, the exact primitive, the exact draw call. So this is the exact fragment that generated that color. And now, just like I did in my CUDA code, I can just sit here and step right through. I can highlight different variables and see what their values are. Exactly the same capabilities you had in CUDA and on your CPU side code, now you've got in your graphics code as well. And so you can debug your shaders, make sure things are working out exactly the way you expected it to, just like you do on your CPU side code. Now one of the things I want to do, another capability that we've added to Visual Studio, because one of the problems you have is you want to kind of figure out the context of what's happening with your draw calls. And so we came up with what we call the graphics focus picker. And what this does is this shows you all of the fragments that are currently in flight. You can see here we've got 30 fragments, 30 paused pixels that are currently in flight. Now what we also did was we synced the context of the frame buffer of the render target from the target to the host at that given moment. And you can select any render target you want. Any one of the bound render targets you can select and you can sync that over. And so now you can zoom in and you can actually look at the different fragments that are in flight. And you can even select which fragment. You can see down here my locals are changing, so my pixel XY is changing as I select the different pixel that I want. So if it happens to be that you didn't choose the exact pixel that you wanted, no problem. You can just come in here and use the pixel picker. And we have the same capability for your vertices and everything. We stream all your models over, and you can look at your model. You can look at that vertex that might not happen to be in the right area and everything. So it's just really some additions that we gave you inside of Visual Studio, inside of the debugging capability, to give you the context that's happening in from a graphics perspective. All right, so let me go ahead and exit out of my debugging capabilities here. Now what I want to do, close this guy, give himself a little more space. Now what I want to do is, let's say we've gone ahead and debugged everything. We looked at our API calls. Everything looks great there. We looked at our shaders and everything. We've inspected everything. We've debugged everything. Everything's good, but maybe the performance is still not quite what you wanted it to be. Well, no problem. We'll just come back up here to the frames page, and I'm just going to say profile frame. So what I'm doing now is I'm running a bunch of targeted experiments on the target to really give you, again, what I was saying earlier, the bottleneck and utilization information at every point along the GPU pipeline. And so we're running like 55 different experiments for every single draw call in the scene. And so it takes a little bit. It's about 3/4 of the way done. And one more. There we go. and now it's going to synchronize all of that data from that profiling run from the target to the host. And this is not a super complex scene. It's got 305 draw calls and 3 compute calls, but it's a decent size, and it took about 5 seconds, so it's not terrible. And so when you come in here, we group all the draw calls by what we call state buckets. And we allow you to edit those state buckets to specify what you feel like is an interesting grouping of the draw calls. And the reason why you want to do this is it allows you to really focus your optimizations on one piece of information, but that will expand and actually improve multiple draw calls. So let's say you're tending to think you're more shader bound. So you can say, okay, well, give me state buckets of draw calls that all share the same pixel shader. Let me just pull this down a little bit. So now what I've done is given you all those draw calls that share a similar pixel shader. So if I make an improvement to this pixel shader, it's going to improve 36 different draw calls. And so it's going to multiply that optimization effort across a whole bunch of different draw calls. Now, just like we showed earlier, all this stuff is still linked. I can come here and click an event. I got lucky there. It was the same exact one. I promise. I didn't plan that. But all the same information that we have from the graphics inspector I can get to. I can get how much time it took on the CPU, how much time it took on the GPU. I can sort these, obviously, and make sure that I'm looking at the most expensive draw calls either on the CPU time or on the GPU time. We also do the same capabilities for your dispatch calls. And so we've got all of your information from your launches, your dispatch dimensions, your group dimensions, and then that same capability we had in the analysis section where we showed you the occupancy for your CUDA kernels. We can show you the occupancy for all of your direct compute. This happens to be running direct compute for all your direct compute kernels as well. So that same capability, that ability to tune your launches to make sure you're really filling the GPU with as much work as possible, we allow you to do here as well. So now what I want to do is focus down here on the data that we give you. So when you first come in, we show you the summary page. And this gives you for all of the draw calls that you've currently got selected. So if I happen to select some subset, again, based on a state bucket, it'll update that for that currently selected group. And it gives you an overview for the utilization and the bottleneck. And these are different points along the GPU pipeline. The input assembly, basically that's pulling in all of my attributes and getting all my primitives ready. My geometry unit, my shader unit, which obviously on a unified shader is going to be running anything from a pixel shader to a geometry shader to a tessellation shader, doesn't matter. My texture unit, so all my texturing capabilities that I've got going on, as well as my blending unit and my frame buffer. And I want to note also that the frame buffer unit is all activity that touches the frame buffer. So that could be your texture unit that's actually reading samples from the frame buffer. That could be blending. That could be reading some of your attributes. So that's basically how memory bound from the GPU's perspective are you in terms of all of your use of the frame buffer. Now what we do is we allow you to weight these based on a couple of different categories. This one happens to be weighted on GPU time. So the idea here is that for my most expensive draw calls, where do I need to focus? And you can see here that I'm utilizing my shader unit about 39%, and I'm about 58% bottlenecked on my shader unit. Now you'll also note, I wanted to mention that these don't add up to 100. And the reason why, one, they don't add up to 100, and two, you usually will not see any given unit go to 100. And the reason why is that a unit doesn't have to be 100% bottlenecked in order for it to be a bottleneck in your scene. What that means is that, in this case, 58% of the time, the shader unit was preventing units above it in the pipeline from sending it work, as well as preventing units from below it in the pipeline from continuing and getting things done. So over half the time, the shader unit was sitting here churning and getting a lot of work done. Everybody else was either waiting because it's like, oh, I can't do anything more. You're preventing me from giving you work, or completely idle. The rest of the units were idle because there was no work to be done. So even though it was only 58% of the time, if you improve that shader and you tune that shader and make sure that it's optimized on the cycles, it's going to make the entire pipeline flow a lot better. Okay, and so even in this case, you could go after the geometry unit and you will see some improvement in your frame rate, even though it's only 18% of the bottleneck. Okay, I want to make sure that's clear. And again, these won't add up to 100 because it's from that unit's perspective. How often was it the bottleneck for the units that were next to it? Okay. So some of the weightings we give you here was give you the ability to, of course, do unweighted. So this is just the raw data. And then you can come in and you can say, okay, based on the number of pixels that a given draw call puts on the screen, weight them. And you can see here, I'm going to tend to be a little bit more shader bound or shader utilized, a little bit more of the texture unit utilized, and a little bit of the frame buffer. And then if I go more on the primitives, this happens to not be a great example, but a lot of the primitives, you can see my input assembly jumped up just a little bit there. So you can, it kind of behaves the way you would expect. If I'm drawing a lot more primitives, things on the input assembly, maybe the geometry unit, there's going to tend to be more utilized, be a little bit more of the bottleneck. And when I'm doing more on the back end, on the pixel side, that's going to be more on the texture unit and the raster operations and the frame buffer and stuff. Some of the other capabilities, we also show you, an overview graph here. So you can come in here and you can zoom in for any given draw call. You can see the information and tooltip over it, get an idea what that is. And by the way, this is all syncing with the target. If you could go to the target real quick, please. So as I selected that draw call, you can see here on the target, it's going ahead. I'm going to change draw calls. It's changing draw calls on the target. So I didn't mention that earlier, but as I scrub on the target, it's synced with the host, and as I scrub on the host, it's synced with the target. So you can be sitting there going, okay, I'm looking at some graph with a whole bunch of data. What is that? Oh, that's what that is. Okay. So you can get a quick at-a-glance view of what's happening on both sides. Go back to the host, please. Thank you. And we have the same capability with the utilization information, as well as, the number of shaded pixels for any given draw call, number of primitives and everything. So it kind of gives you all the statistics you'd want to have in order to be able to kind of get an idea of what's going on with your scene and make sure that you're focusing your profiling efforts. I think that's about it. Let's go back to the slides. Excellent. There we go. Excellent. Thanks. So with version 2.0, which just went out a month or so ago, right? Somewhere in there? Yeah. Some of the new capabilities we put in there, and I didn't have time to show them because obviously it was a lot to see. We put this new capability to view all of the graphics resources at a glance. So the idea here is that we give you all of the textures, all of the render targets, and you can see how often a given texture or render target is used. You can see a thumbnail of it, and you can zoom in and all that kind of stuff. So rather than having to go draw call by draw call and inspecting every texture, now we give you a gigantic list of all of the textures and all the render targets, and you can see the information. And you can sort. You can sort by usage. So you can look for things like, well, maybe I have a texture that's not even used in my scene, and you can look for things like that and make sure that you optimize that. Lots of usability and workflow improvements. Hopefully they came out here. We also really worked hard on the graphics profiler. It used to take literally about 5 times longer, and so we really worked hard to optimize and utilize all of the GPU capabilities that we have for gathering that information and give it to you. And also we did lots of targeted testing to make sure that the information that's coming from the profiler is accurate. So we really wanted to focus and make sure that we're giving you guys the information you need. Another thing we introduced was what we call driver independence. So back in the day, we used to have these concepts of instrumented drivers and everything, and that was, good for us, not good for developers. So we got rid of the instrumented drivers, and then we said, okay, we're going to have, separate drivers for our tool, or, have our tools work with the web drivers. But then the problems we ran into is when a next version of a driver came out, well, then we have to put a next version of the tool out. And so we were lockstepped with the drivers, and then we have maybe have somebody who's like, oh, I have to use version X, but I want to use this new version of the driver, and now I can't use the tool anymore. So what we did was we put a layer in between the tools and the drivers to make sure that we're completely independent. So if you want to go and like right now our 275 drivers are on the web. If you want to go and install a 280 driver, which are beta on the web, no problem. It's going to work just fine with Parallel Nsight. So we wanted to make sure that you guys can update as you see fit rather than having to lockstep with our tools. Again, lots of stability improvements and, again, support for the latest hardware. We introduced support for all the latest the notebook drivers, the GF119. What is that? It's a Quadro 4. I mean, yeah, it's Quadro 400. All the latest Quadro boards and notebook boards and everything are all supported in Parallel Nsight for all of these capabilities: the debugger, the profiler, all those things. On the compute features, we introduced support for the CUDA Toolkit 4.0, and obviously we did full Visual Studio 2010. It works with both Visual Studio 2008 and 2010. We also introduced the support for the Tesla Compute Cluster, or TCC. What this allows you to do is it allows you to have a GPU in your system that is headless. It doesn't actually have a monitor connected to it, and it runs with a different driver. It doesn't actually run with a normal display driver. It runs with a really lightweight compute driver. And so that's one of the things that allows you to do that same machine multi-GPU debugging capability that we saw earlier in the slide when you're doing CUDA or compute debugging. And so we added support for that TCC capability. Also, we had the PTX assembly debugging. I showed you that earlier. So you can show your PTX code right in line with all of your source code that's going on, and you can even step through that. You can also attach to a process, which is really great. If you've got a process that's running that you launched and you didn't launch it under Visual Studio, or didn't launch it originally with Visual Studio, no problem, you can attach to it later and still debug just like you did all your CUDA kernels. We don't support that in graphics yet. It's something we're working on, but we do support that for CUDA. Again, lots more improvements for those metrics and experiments. We finally allow, or we're able to allow concurrent kernel trace. Before, what we did was when we did the tracing, we actually made it so that the kernels launched serially. So we launched a kernel, then launched a kernel, then launched a kernel. And now, as you saw here, all the kernels are launching concurrently. So if you happen to have multiple kernels running at the same time, we can trace that and give you the information as it's running. Again, the API trace, all the conditional breakpoints, so now you can set conditional breakpoints based on your local variables in CUDA. We supported that before in graphics, now we support that in CUDA as well. And again, same thing, we support the latest drivers and hardware. So to wrap up, again, thanks everybody for coming. We definitely appreciate you spending your time with us. Please do download Parallel Nsight and give it a shot. Send us feedback, any features that you might want. We are going to be here at SIGGRAPH. I'm here. My boss Sebastian's over here. Feel free to come up to us. Give us feedback. Any features that you want. Any things that don't work for you. We definitely want feedback, especially on the working with multiple systems. If that happens to be a problem with you, let us know that so that we can make sure that we prioritize the feature set that we've got, and obviously come up with your ideas to make sure that we're doing things in the order that you want them to make sure they're meeting all of your needs. And obviously, you can contact us as well at the NVIDIA Developer Forums. We've got somebody manning those, I promise. We didn't for a long time. We now have somebody manning those. And so any feedback that you give there, it will come to us, and we'll make sure we incorporate it in our roadmap.